Lecture 5 online, Families of Data Variation, Problem Debug, and Improvement. So, between our in-class lecture and the book, we've been working on answering the following questions. Firstly, how many digits are real? And this involves the topics of significant figures and probable error. Another question, well, how well can I see what's going on? And this deals with insufficient sig-fig or chunky data. And also the topic of discrimination and the number of distinct categories, or NDC. But now I want to ask this question. How many parts should be measured to verify the measurement? And this speaks to measurement consistency. And this will be the topic of Chapter 5's online lecture. And it's a question that I'm often asked. Folks want to establish some sort of measurement consistency. But how do you know how many parts to pick? Many solve the problem through habit or superstition. We've always measured 10 parts. That's what we've always done. It's 10 parts. You must select 30 parts to know if your process is in control. Or how about this one? Maybe 2 or 3. It's pretty much what I choose. My answer, on the face of it, may be even worse. Wait for it. It depends. I know. It depends upon how much uncertainty you can withstand and how much certainty you need. And this incorporates the statistical concept of producer and consumer risk, and we'll talk about that in a moment. It depends on how much meaningful difference there is between the parts and the groups of parts you're looking at. And finally, it depends on your measurement system. Is it well controlled? And are the associated measurement uncertainties well understood? Generally, acceptance sampling is when you decide to accept or reject a lot of parts based upon the results of inspecting a few samples from that lot. Ideally, there is a good/bad boundary based upon some metric. But as we've learned, there are always measurement uncertainties that creep in and muddy the water. Depicted here is what is known as an operating characteristic curve, also known as an OC curve. The ideal sampling line reflects the error-free measurement boundary. That is, if you could achieve measurement perfection each time you grabbed and checked a part, then you could conclusively decide the good from the bad, and maybe even the ugly. The thing is, there's always error, and so we know there will always be some uncertainty in differentiating the good from the bad. So let's first talk about producer's risk. So on the graph, starting from the left-hand side and moving to the right, you can see that as the parts get closer and closer to the good-bad boundary, we, being the stand-up producer that we are, begin to prematurely reject parts such that we never send a bad part to the customer. You can see that in the little triangle, the little red triangle there, where the parts would otherwise be considered acceptable are set aside as being suspect. It's similar to the application of gauge maker's tolerance on our go, no-go gauges. This is known as producer's risk, alpha, or type 1 error, and is referred to as the producer's risk because the producer made the good part, yet he rejected it. The risk, I guess, is to his bottom line. Now on to consumer's risk. Again, moving from left to right on the graph, we see the customer being completely satisfied by not receiving bad product, bad being a relative term, but at some point the customer begins to accept parts that are, well, maybe good enough. The parts in the yellow triangle are good enough parts because they were accepted by the customer, but they weren't a spec, and the customer might not know that. This is known as consumer's risk, beta risk, or type 2 error. And we can consider it the consumer's risk because the consumer has accepted the parts and the associated risk when the parts should have been rejected. Now they may work in the application and they will likely result maybe in some more waste or rework than the customer had anticipated. These parts, they just don't seem to work as well as the last batch. How many times have we heard that? Or maybe it's the machinist, our producer, who walks up to your desk, you being the consumer with a bag of parts, and says, can you use these parts? I think they'll work just fine. Yeah. Now, There's an entire field of study behind something called AQL, acceptable quality level, and it seeks to define how many, quote, bad parts you are allowed to find before you reject the lot. The work presented here is a component of this field of study. The thesis here, though, is that it is possible to define the number of parts that should be measured so that you know you have a verifiable measurement difference from one group of parts to another, or from one batch of parts to an expected standard. So let's think about this in terms of distributions. Okay, and there are aspirationally hoped for distributions, and then there are hard, cold reality distributions, all right? So looking at the above distributions, the goal distribution, that's our aspirationally hoped for, right, is the standard we're shooting for. It has a desired variance and a desired average. Now the actual is from the parts we actually have in our hands. It's the hard, cold fact distribution, right? It has a known variance and a known average. So let's say our goal is an average of 6 millimeters plus or minus 2.4 millimeters. Those are our specification limits. All right. So we run the process, right? We grab a part, and measure it, and it measures 9. And we say, aha! Our process has mean shifted. Our actual average and variance has shifted. Reject the lot! But a measurement of 9 could, and in this case did, come from the red zone, the tail of the goal distribution. We are running according to the goal distribution. We just happened to pick an outlier, one of the parts that was in the tail. So we're at risk of rejecting the entire lot of parts when 90% of the parts will be good. While our part is out of spec, the process has not shifted, and therefore it is a false rejection. It is known as a type 1 error alpha risk or a producer's risk. And before you say, but Professor Bana, this process is not possibly a plus or minus 3 sigma control, I'm going to say, yes, you are right, but the example still stands. So this time we run the process and grab a part and measure it, and it measures 7. And we say, woohoo, yes, we are good, these parts are great, the lot is accepted, ship it. But in this case, the part came from the yellow region of the other shifted actual distribution. Yes, the part is the spec, but what we don't realize is the process has actually shifted here. And there will be other parts in the pack box that will be out of spec, perhaps as many as 74% of them. And yes, while the part is in spec, we are blind to the process shift. This is called false acceptance. It is known as type 2 error, beta risk, or consumer's risk. Now this topic will be covered in greater detail in your Probs and Stats class, but the concept here is important in order for you to have a high level understanding of meaningful differences in measurement. So clearly, grabbing one part and measuring one part and making a decision utilizing one part comes with risks. Okay, and so now the question of how many parts you need to measure is a good one. We saw from the preceding example that a sample size of 1 did not capture the risk of missing important variation. Didn't cover it, right? So now NIST to the rescue, has provided a straightforward table for the selection of sample size. Now, it requires the user, that's you and I, to make some decisions/assumptions, and those are as follows. Okay, first, the value for alpha, that's the alpha risk, the risk of rejecting a true hypothesis, that's aka producer's risk. This is sort of our confidence level for the test. We will typically select alpha to be at 0.05, which is basically a 95% chance of catching it, right? 95% chance of catching the problem, catching the shift. All right. Now, the value of beta risk, right? Of accepting a false null hypothesis when a particular value of the alternative hypothesis is true, Again, this is a lot of fancy words here. This is our consumer's risk. This is of missing the failure, missing the shift, right? We're going to give ourselves a beta of 0.1, basically a 10% miss rate, okay? It represents the risk of failing to detect a difference for any group of measurements, one from the other. Okay, so it's 95% hit, 10% miss. That's what we're setting up. And yes, these do seem kind of wide open, the 95% hit rate and 10% miss rate. But remember, we're looking at the averages of a number of parts that are going to be checked, right? And the distributions that are associated with those parts, and not any one single part. Get measuring one and done, get that out of your heads, all right? Now, a couple of more things. We need to know the value of the populations, and that's plural possessive, the populations standard deviations. If it's a goal, we'll know what we want the goal distribution to be, the standard deviation to be. If it's the actual part, we can measure that and calculate that, right? Okay, and delta then is the difference or shift from one group to another, or from one population to another that we wish to detect. How far apart are they? Remember those previous diagrams we saw two distributions, the goal and the actual. Del was the difference between those two. And you can imagine the closer and closer those two are to each other, the more samples you will need. Now, this method, I agree, it's high level. It's arguable in that you can get a group of mathematicians in the room and they're going to argue with the engineers on this one. But in this case, I am both a mathematician and an engineer. I had the argument with myself, I won, and I believe it's a workable methodology. So let's deconstruct the table here. Alpha, being our producer's risk, is in the first column. It ranges from at the tippy top there, 0.01, which is a 99% confidence of our getting it or catching the difference, right? All the way down to about a 0.2 or 80% confidence. The delta columns that have that funny little squiggle, that del in them, that's the difference or shift in the sample population that we wish to detect. And it's expressed as a function of population standard deviation, sigma t, or total variation that you might see in like a gauge R&R. Right? So it's interesting to note that as we become more concerned about producer's risk, we need to increase the number of samples we wish to measure. So if we want to have a really, really great confidence, like a 99% confidence, you can see that as you go up, more and more confidence requires more and more parts to measure. Well, that makes sense. That makes intuitive sense, right? Look to across the top of the differences there, those dells. The smaller the difference in population we want to detect, the more resolution we need, the more samples we have to check, which makes sense too. Think about our two previous examples where we showed two distributions. As those distributions creep closer and closer together, as del gets smaller and smaller, the overlap between those two distributions grows. It makes sense you have to select more samples to see it improve if you're in one distribution or the other. Now, there's a final twiddling knob here. That's this beta knob, right? This is the consumer's risk. That's the mistake risk limit knob. And we twiddle that to establish how much risk we're willing to have the consumer take here, right? Again, the more concerned we are with risk we become, the more samples we need to measure and evaluate, right? So, the section we're going to focus on here, the one we're going to use, that you'll use going forward, is kind of the 95-10 row, right? It's at 95% confidence, a 10% miss rate. 95% hit, 10% miss. That's the row you can see here that we're going to kind of focus on. So now for an example. So let's try a typical 6 sigma sort of problem. For all of you 6 sigma warriors out there, one of the premises is that normal production variation will shift the mean of the production population by plus or minus 1.5 standard deviations on an ongoing basis. Right? So total variation from our X bar R gauge R&R is an estimate of sigma t. In this example, it was found to be 1.146. So we're saying that our total variation that we would expect is 1.146 to standard deviation, right? This includes then all the variance of the population, the parts, appraiser, measurement equipment, right? Del then is the difference or shift we want to detect. So let's choose the typical 6 sigma assumption that the mean will shift 1.5 sigma. That's the difference we want to detect. So more specifically, we want to be able to detect when the distribution has shifted more than 1.5 standard deviations from the goal distribution, because when it has, we're going to be worried about the process that's running properly. So that puts us in the 1.5 sigma column. That's the one we're going to use, and you can see I've got it highlighted there. Now, we'll use our typical 95% confidence limit and our 10% miss limit, beta equals 0.1, for the group of measures. And you can see there's the group we've taken. We're at alpha 95%, beta 0.1, and the del column 1.5, and shazam, we need to triangulate on and measure 5 samples minimum. If you measure 5 samples, that should be enough to tell you whether the distribution has shifted plus or minus 1.5 sigma. Now, that's the minimum. What this says is that if there is a 1.5 sigma mean shift from your normal process distribution, your measurement system, right, with 5 samples should be able to detect it. Now, I'll go one step further and say that with a random selection of 5 samples from a manufacturing process, if you measure no variation at all, it's likely time to question your measurement system. Can we say chunky data? Not enough resolution or discrimination? Maybe somebody dropped the gauge? Any one of those things. It's the beginning of a measurement system debug process. Okay, so between the in-class lecture, this online lecture, our lab, and the book I've given you guys, chapter 5 there, we have discussed each of these questions in grave detail. First, how many digits are real? And that had to do with the concept of sig fig and probable error. Then we discussed, well, how well can I see what's going on? And that's with the data, of course, the measurement data. And that discussion involved insufficient significant figures, or sig fig, or that whole idea of chunky data. And also we talked about discrimination and NDC, number of distinct categories. And now finally we talked about how many parts should be measured to verify the measurement. That was the whole idea of the del and 2 distributions, the goal and actual, right? That was that measurement consistency and the magic number that we're looking at often. Now, it's very important, right? There's a very important question in the book, chapter 5, page 56, book, right? You need to make triple dog sure you thoroughly understand the components of the question and can confidently answer it, because you will see it again. And there you have it, our online portion of Lecture 5, Families of Data Variation, Problem Debug, and Improvement. All right, gang, see you all in class.